BPSC aspirants, warm welcome and join the session question answer discussion series और इस क्वेश्चन आंसर डिस्कशन सीरीज का मुख्य उद्देश्य है आपकी राइटिंग स्किल को बढ़ाना, अच्छा करना ताकि अच्छे आंसर लिखे और अधिकतम मार्क्स आपको आ सके। कारण यह है कि कम शब्दों में और कम समय में व्यापक विषय पे आपको उत्तर लिखने होते हैं। ओके, so now let us start the discussion. Our question is here. India has achieved remarkable successes in unmanned space missions, including the Chandrayaan and Mars orbiter mission, but has not ventured into manned space mission. What are the main obstacles to launching a manned space mission, both in terms of technology and logistics? So here is a reference up to unmanned space mission, Chandrayaan and Mars orbiter. India has now, let us start this session. India has achieved impressive success with unmanned missions such as Chandrayaan and Mangalyaan, demonstrating precise navigation, launch capability, and deep space operations. Sending humans into space, a crewed mission, however, is a qualitatively different challenge. It needs not only rockets, but also the guidance system, along with the comprehensive life support, safety, medical, and recovery systems, and the social, institutional, and financial support to sustain them. Below, I list the main technological and logistic obstacles, so-called impediments. Examine them critically and assess how they can be addressed. So come back. Major technological obstacles or called the impediments. Technological impediments or obstacles. When human rating launch vehicle, what it means? Ensuring the rocket is safe, extremely reliable, and has redundant systems so a human can survive launch efforts or failure. Challenges as regards human rating the launch vehicle. Challenges: structural margins, engine redundancy, fault tolerant avionics, vibration acoustic limits for crew conflict, and qualification testing for beyond typical unmanned standards. So, New escape and abort systems. What it means: systems to pull the crew module clear during a launch failure, paired abort, ascent abort, and issue safe descent. Challenges: integration of a fast, reliable launch escape system. So LES, launch escape system. Timing and sequencing logic and validated escape trajectories. 3. Life support and environmental control. ECLSS. What it means? Providing breathable air, pressure, temperature control, shear assembling, water recovery, waste management, and fire suspension for the duration of the mission. Challenges: long-term recycling, small volume systems, reliability and validation under real mission conditions. 4. Thermal protection and re-entry systems. What it means: safe re-entry of the Q module through atmosphere, heat shields, controlled deceleration, and landing CS systems. Challenges: designing, testing, and qualifying heat shield materials, precision re-entry guidance, shock or impact mitigation for crew. 5. Radiation protection and human health in LEO or deep space. What it means: shielding and operational limits to protect crew from solar particle events and the ground cosmic radiation. Challenges: effective shielding versus weight constants, monitoring, and medical countermeasures. 6. EU systems and human factors engineering. It means spacesuits, crew causes human machine interference, cabin ergonomics, habitability for psychological health. Challenges: designing suits for intravehicular and extravehicular activities, habitability for confinement, and interfaces that minimize human error under stress. 7. Medical support. We are talking to the constants, that is the obstacles. Medical support and emergency care capability. It is in-flight medical monitoring, diagnosis and response capability for acute problems, cardiac, trauma, decompression sickness. Challenges are training queue for medical emergency, compact medical kits, telemedicine, latency and limits. 8. Docking, rendezvous, and orbital operations if needed. It means precision, orbital, mechanics and hardware if missions involve orbital docking or rendezvous, that is ISS visits. Challenges are very tight tolerances, autonomous systems, and crew training. Now come to the major logistic and institutional obstacles, cost and sustained funding. It means crewed programs are expensive. Development, testing, training, operations need sustained multi-year funding. Challenges are allocating large budgets while balancing other national priorities, political continuity. 2. Ground infrastructure and recovery capability. It creates crew training centers, neutral buoyancy pools, flight simulators, mission control with human flight experience, recovery ships for the teams, medical or the hospital readiness. Challenges are building or upgrading facilities, training large technical and support personnel pools. 3. Human resources and specialized expertise. It means aerospace medicine, flight surgeons, human factors engineers, spacesuit designers, ECLSS specialists, and operation crews. Challenges here: creating and retaining this specialized talent, cross-disciplinary training between ISRO, medical and academic institutions. Then 4. Regulatory safety culture and liability frameworks. What it means? It means rigorous safety certification, independent review boards, astronaut health standards, and insurance or liability arrangement. Challenges relates to establishing transparent oversight, risk communication in public, and legal frameworks for crewed launches. 5. Training and astronaut selection. What does it mean? It means long resource-intensive training programs, piloting, spacecraft systems, survival, medical, EVA practice. Challenges are time and cost to train crews to operational readiness, psychological selections, and the testing. Now 6. Public acceptance and ethical concerns. What it means? It means societal tolerance for perceived risk to human life, use of funds, and environmental impact. Challenges led to high visibility failures can undermine public support for space programs. Now come to the critical ambition, strengths, weaknesses, trade-off. Strengths India already has proven launch and mission design expertise from reliable unmanned mission, navigation, cryogenics, propulsion. Next point is cost-effective engineering culture demonstrated by low-cost lunar and Mars missions. Then growing industrial base and partnership that has the leverages for hardware manufacturing. Now weaknesses and gaps to breathe. Limited human-related system heritage. ISRO has far more experience with robotic than human systems. Narrow experience in life support, human factors, and crew medical assistance. Infrastructure gaps, that is, large neutral buoyancy facilities, dedicated astronaut training centers, and recovery fields for mass rescues. Then come to trade-off and risk. If speed was safety, rushing tests to meet schedules increase risk. Human missions demand conservative, timeless, and extensive unmanned test flights. Indigenous versus international cooperation. Full domestic development builds capability but is costlier and slower. International partnership can reduce risk and time but raise technology transfer and strategic issues. Now come to how obstacles can be addressed. Practical steps. Adopt a phased approach. Begin with incremental unmanned test flights of crew module, abort system, re-entry, and life support elements before committing to crewed launches. Next point. Invest in infrastructure and human capital. Build training facilities, simulators, neutral buoyancy, strengthen aerospace medicine programs, and create interdisciplinary teams with universities and hospitals. Then come to robust testing and redundancy. Emphasize redundancy, compound burn testing for skill qualification and independent safety reviews. Now look at the international collaboration with CESUR, international collaboration. Partner for specific capabilities, say space medical protocols training, while retaining co-mission systems within national control. Next point. Create a mature safety and regulatory ecosystem. Establish an independent human space flight safety board. Transparent reporting and legal frameworks for crew safety and liabilities. Now come to the point, public engagement and transport risk communication. Build public trust through outreach, clear explanation of benefits, cost, risk, and mitigation strategies. Now to conclude, conclude. Launching a human space mission is technologically and organizationally far more accomplished than robotic missions. The obstacles, strong rocket engineering, crew safety systems, life support and medical preparedness, training, infrastructure, and institutional readiness all require sustained funding and a strong safety culture. That said, India already has many foundational strengths, say proven rocketry, cost-efficient engineering, and a growing ecosystem. With a phased safety first program, targeted investment in human system and training, and selective international cooperation, India can overcome these obstacles. The key is patience crewed spaceflight demands time, repeated unmanned validation, and uncompromising attention to human safety. That's all for this lecture. Thank you.